Just as to express a line using an equation, we need a point and a direction. In order to express a plane using an equation, we need a point and a direction. The point is generally not too tough. However, there are an infinite number of lines that exist on a plane, and so trying to use a line to give a direction for a plane is a little bit tough considering lines in the plane. So rather than do that, what we're going to do is we're going to set up a coordinate system, and we're going to use vectors. We'll say that the vector in standard position r sub 0 corresponds to a fixed point on the plane, and so we'll say that r sub 0 is x naught, y naught, z naught. We'll consider any other point on the plane and a vector that goes to that point. Again, the vector is in standard position. We'll call that vector r, and it's generic. We'll give it components x, y, z. So the head of the vector r naught, x naught, y naught, z naught is a fixed point on the plane. And the head of the vector r, which is x, y, z, is any other point on the plane. We can create a vector that goes from the head of r naught to the head of r. And that vector is going to be r minus r naught. We saw something like that in a previous video. And boy, now we've done it. We've got one vector in the plane, a couple of vectors that aren't in the plane, but their heads are. What does this have to do with the direction for a plane? It turns out that while I can't express the direction using a single line within the plane, I can express the direction using a single vector that is orthogonal to the plane. You see, while there are multiple angles within the plane for any lines to exist on, there's only one right angle against the plane. We call that vector n. We're going to give it components a, b, and c, and n is the normal vector to the plane. It indicates a direction for the plane. Now each plane actually has two normal vectors. The other one would point in the opposite direction, and we're not going to bother ourselves with which one we're dealing with. We can always use either one. Now, because n is normal to the plane, it's orthogonal to the vector r minus r naught. So r minus r naught dotted with n is going to give us 0. They're orthogonal vectors after all. This is going to give us the equation of our plane. The vector r minus r naught is expressed as x minus x naught, comma y minus y naught, comma z minus z naught. The vector n, we said, had components a, b, and c. And we're going to find the dot product, and we know that that dot product is going to be 0. Computing the dot product gives us a times the quantity of x minus x naught, plus b times the quantity of y minus y naught, plus c times the quantity of z minus z naught is equal to 0. The components a, b, and c are the vector direction, the direction vector for the plane, and the points x naught, y naught, z naught are a point on the plane. Well, they're the coordinates for a point on the plane. By distributing and collecting like terms, we're going to get ax plus by plus cz is equal to d. And this is the standard form for the equation of a plane. You'll note that there's a similarity here between the a x minus x naught plus b y minus y naught plus c z minus z naught. If we didn't have that z component, then this would look very much like the equation of a line on the plane, the xy plane, that is. Let's see how we might use an equation like this to visualize part of a plane. We're going to visually represent the portion of the plane 3x plus 4y plus 6z equals 12 that is in the first octant. And we're going to do so using intercepts. If y and z are both 0, then we get 3x is equal to 12, and so we have an x-intercept of 4, 0, 0. If we let x and z be 0, then we have 4y equals 12, and so we have a y-intercept of 0, 2, 0. And if we let x and y be 0, then we end up with the equation 6z equals 12, and so z equals 2. And so we have a z-intercept of 0, 0, 2. Representing this in the first octant, means I really just need to form a triangle in space using those 3 points. And here is the plane. Now it extends in all directions here, but we're just looking at the portion of it that's in the first octant. As for the normal vector, for any point here on the plane, we can imagine a vector that sticks out from the plane at a 90-degree angle. And the direction vector, that normal vector, is 3, 4, 6. And so that vector has a component in the x direction of 3, the y direction of 4, and a z direction of 6. We won't be graphing planes very much. I just wanted you to see how that worked out.